Hi everyone, in this video we're going to go through pseudocode again. So this is the second video on pseudocode. So just make sure that you go through the Ed Rollo theory and videos on Newton's method of approximation and the bisection method, because we're going to be using them in this video, and it'll probably make more sense what I'm talking about once you've watched those videos. So I'm going to scroll on through the theory because we've already done that, and the questions we've already done. Now the previous video we did some multiple choice, but we're actually doing some more multiple choice here. I just realized there's more multiple choice questions, and I think these are from the practice exam, but the more we can do, the better or more familiar you will be with what sort of questions they will ask on the exam. As I said in the previous video, I highly think there's going to be a multiple choice question, and there could also be a extended response question on pseudocode. And in exam 2, you will see pseudocode. You won't see it in exam 1, and as well as Newton's method of approximation in exam 2. So it's probably a good idea that you understand how it's used in Newton's method of approximation, and the bisection method are used in pseudocode. Okay, so let's make a start. So question 5. So the algorithm below described in pseudocode estimates the value of a definite integral using trapezium rule. So the trapezium rule is on your formula sheet, but here it is used in pseudocode. All right, so your input. So we've just got our function, which is going to be defined later on. A is our lower terminal of integration, B is our upper terminal of integration, and N is the number of trapeziums to use. So basically we're going to have our definite integral, all right, which is f of x, and we're going from A to B, but we're approximating using the trapezium method. All right, so in the define part, it is basically stated where everything is. So we've got our function. So if I just go down, put this here, so it actually tells us that we're going to be using a log function. So f of x is equal to log base e of x. Then we've got our value of a. So a is equal to 1. And b and n. So do that here. So b is equal to 3 and n is equal to 10. So a is just your lower terminal, b upper terminal, and n is the number of trapeziums, so which is important to note. All right, so when we're using the trapezium rule, right, you can see that we're substituting in b minus a divided by n for h. All right, so basically h is equal to b minus a divided by n. And then we've got the sum is equal to f of a plus f of b. And we're going to let I equal 1. All right, so then we've got a while. So what this means is we loop through this until we get to the end. So we're going to end when, until we're going to keep going until we reach I is less than 10. So when I is 9, we're going to that's going to be our last one, because n is equal to 10. So we're going to keep going through until we stop at 9. All right, but let's just see what the question asks. So it's obviously we wouldn't be expected to do 9 iterations. That is just way too long. So the question is actually asking us to find the value of the variable sum after 1 iteration of the while loop. All right, so we just want the sum part. Okay, and we're doing just 1 iteration. So that just means we're going through the pseudocode just once, or through this while loop once, which is here. All right, so let's do that. So first of all, doing our sum. So sum is equal to, so sum plus 2 times f of x. Now you'll notice in your up here where we've done our define, that sum is equal to f of a plus f of b. Whoops, f of b 2 times f of x, so x is equal to a plus h. I'm running out of room here. I'm going to squeeze it in, a plus h. Alright, so here we've just substituted everything in for sum. Alright, so we've got f of a. I would probably do this straight onto the calculator, not on the page. So a is equal to 1 plus f of b, and b is equal to 3 plus 2 times f of a plus h. So a is equal to 1, sorry, I'm just thinking, and then h, which I could have written down here. So we've defined h here. All right, so I just need to do that. So we're going to have b minus a. So b is 3, a is 1, divided by n, which is 10. So we're going to have 3 minus 1 is 2, divided by 10, which is 1/5. All right, and we can just put all of that into the calculator. All right, so I would just define it. You don't necessarily have to. Now you can use ln for log base e of x, just a little shortcut for you. All right, and then I'm just going to put all that in. So I'm just going to pause while I do that. All right, so after defining it, I've just put in exactly what I wrote on the page. So f of 1 plus f of 3 plus 2 times f of 1 plus, well, 0.2 is the same as 1/5, and we get 1.463. So there your answer is C. Oops, let me circle you. All right, so there's an example of just, you don't have to keep going through the loop, and if we did it, it's going to be quite time consuming. So we only have to do one iteration, all right, to find what the sum is. All right, moving on to the next question. Sorry guys, come on, let me scroll. There we go, question 6. All right, so consider the algorithm below, which uses the bisection method to estimate the solution to an equation in the form of f of x equals 0. So we've got our inputs here defined up the top. So f of x is our function. So if I go down here, you can see that f of x is sine x. A is your lower interval endpoint, and b is your upper interval endpoint. So we've got a and b here. Because you can also see it's been defined here, I should have mentioned that. So f of x, comma a, comma b, and then your maximum. So the maximum number of iterations. And for this one, we're doing 2 iterations. All right, so there's your pseudocode. We can see that it's the bisection method, it's been defined there, and it says later on what our function is, what a is, b, and max is. And we're going to start off with assigning I to 0. What else has it told us? All right, and we're going to use a variable mid. All right, and then we'll just go through the pseudocode. So which value would be returned when the algorithm is implemented as given? So basically we have to go through the 2 iterations, all right, and then see what we get at the end. So let's just go through this similar to how we went through it before. All right, sorry, when I said before, I mean the previous video. So we're just going to write everything down. So our function is sine x, our value of a is 3, b is 5, and our maximum is 2. So that 2 means we do 2 iterations. So we go through the loop twice. All right, so that we're going to start off with I equals 0. So that's going to be our first iteration, and I equals 1. All right, so there are 2 iterations. We don't go to I equals 2. So an iteration, because this one is starting at 0, which is here. So our first iteration is at 0, and our second iteration is at I equals 1. All right, so for I equals 0, let's just calculate our mid. So remember, oops, all right, mid, not m. Mid is equal to a plus b divided by 2. So a is 3 plus 5, and then we divide that by 2. All right, so that's our value of our mid, which is 4. And so then we've got mid. If your mid is equal to 0, which it isn't, it's equal to 4. So we would return mid, but it's not. So then we go to this else if, and we test it doing f of a times f of mid. So f of a, where is 3, times f of mid. So your midpoint is 4. And I've already done that on the calculator, so I know that it is less than 0. So when it's less than 0, your b then becomes your mid. All right, so b changes from 5 and now becomes 4, which was our midpoint, which we calculated here. All right, so b changes. If it was greater than 0, so if this part here was greater than 0, then we would change a to our midpoint. All right, so then for your second iteration, let's kind of go around it a bit. All right, so your mid, all right, so remember your mid formula is a plus b divided by 2. So we're going to have 3 plus our new b, which is 4, divided by 2, which is 3.5. All right, so going through our pseudocode, it is not equal to 0, so we keep going. So we test f of 3 times f of 3.5, and I've done that before, but you just do it on your calculator, and it is less than 0, so that means b is now going to change to 3.5. All right, and we've done our 2 iterations. So the value that will be returned is 3.5. Whoops. All right, so moving along, do I have any more questions here? All right, so here we're going to look at Newton's method of approximation. So consider the algorithm below, which uses Newton's method to estimate the solution to an equation of the form f of x equals 0 with a tolerance of 10 to the power of negative 4. All right, so we've got a function, all right, which will be defined later on. Let's just have a look. Here it is, 5 minus x cubed. No, sorry, I should have shown here, f of x. And x0 is an initial estimate for the solution. So hopefully you've watched the video on Newton's method of approximation, and you would know that you have a starting estimate. So a number that you would start off with. So that's just what x0 is. All right, so we've defined Newton's method. So f of x, comma x0, so that's down here. So there's our function f of x, and our x0 is 1. We've got dfx, which is our derivative of f of x, and x0 is what value you're assigning, what estimate you're using. All right, so going down, just before we do the pseudocode, I'll go through the algorithm. So we want the output after the second iteration of the while loop. Okay, so we're going to go through it twice. All right, so let's just follow the steps. All right, so first of all, I is equal to 0, and then we're going to do I is equal to 1. So we're just going to do 2 iterations. All right, so I will always be less than 100 because we're only doing 0 and 1. So this next line here comes from the formula for Newton's method of approximation, which is also on your formula sheet. So I just had a quick look for the formula sheet so you can see it here. All right, so we're going to do another question shortly on Newton's method, but you should have seen this in the Ed Rollo video too. So this is basically all that line of pseudocode is. So x next minus x, oh sorry, wrong one, x current. So x next, so x n plus 1 is equal to x n minus f of n minus the derivative, whoops, not of x, of n. All right, so that comes from your formula sheet. All right, so we're starting off with 0, I think it was. No, it wasn't 0. Where was it? 1. All right, so here we assign x0 to be 1. So I can just do this on my calculator. So defining the function, I forgot what the function was, 5 minus x cubed. All right, so we're going to define f of x equals 5 minus x cubed. All right, and then we're just going to plug all this into the calculator. So xn, so our starting value is 1 minus f of 1, and then the derivative actually, let's delete that. Do it up here. All right, so we want a derivative at a value. So I'm just going to type in f of x here. Find it on the menu. Come on, it's this one. So frustrating, doesn't like me pressing buttons on the computer. All right, so we're just telling it to differentiate f of x. We've already defined it in the calculator, and we want the derivative at 1 because that's our first value of n. It mustn't like me writing it like that. All right, let's do the derivative first. Sorry guys. Oh, what's wrong? All right, I think I had the cursor up in the working out, not on the new line. So there it is, -3, which now that I've done it, I probably think it's easier to do by hand. And you can see how it's not that difficult to do Newton's method by hand. This is a cubic function. I think if you were expected to do it by hand, you wouldn't get a function that was that difficult to do anyway. But Newton's method of approximation is only on exam 2, so you don't need to, sorry, and pseudocode is on exam 2. All right, so let's plug in that. So 1 minus, starting again, so f of n over -3. All right, and you can see it's 2 1/3. So we should really leave it as exact values. Oh, if it wants to, well, I know it's 2 1/3, or 7/3. Okay, so that's, oh, go away. So our first iteration, we get 7/3. All right, so I've just had to delete a huge chunk because I made a mistake. So we've got this 7/3 after our first iteration. So once we got that 7/3, we just got to make sure we keep going to the end, which I didn't do, so I can't remember whether we tested it, but 7/3 is not in between these two values. Sorry, not 7/3, x next minus x current, so that this part just means 7/3 minus x current, which is 1. All right, which is 4/3. So that doesn't meet that criteria. So we go to our else. So we're going to assign 7/3, which is what we just calculated, and then substitute that into our Newton's method of approximation formula. We can return f of 7/3, but we're going to go through another iteration anyway. So I can return that, but we're going to do a second iteration. All right, so going back up, so we're going to use the same formula. So this one here that we did before. So basically, we're going to start with our xn, which is 7/3, minus f of 7/3 over the derivative when x equals 7/3. So we can do that, all that on the calculator. Now I did it before, I didn't get the right answer, so let's try it again, make sure I don't get the wrong answer. All right, so we'll just move that over. So 7/3 we'll plug in later. Let's do f of 7/3. So I'm just going to do everything separately. So I feel like, because I was trying before to do everything at the same time. All right, so we're going to do f of x at 7/3. All right, and so then we can do this calculation. So we're going to start off with 7/3. So just this one that you can see on the right side, minus, and we put that on our numerator, and this on our denominator. And I'm just going to change it to decimal just because it's a bit easier to see. All right, so we get 1.86. So let's just have a look. So it's about 1.86. All right, so let's just do the test here like we did before. So 1.86 minus 7/3. That's not going to fit between those two because they're very small numbers. So we're going to go to this else. So because we're only doing our second iteration, we can then finish up with our return. So f of that 1.86, which I'll just do on the calculator, and make sure you collect all those decimal places. Whoops, let's present it twice. So negative 1.45. Not 2. Okay, so there you can see answer number C. Answer number C. Answer C. All right, now we're going to do a question from a trial exam. I'm just trying to think where I had it open. This one here. All right, so this question we're going to do from the 2023 Inside exam. So question number 3. Now this question I quite liked because we had, it looks at the bisection method and also Newton's method of approximation. So a good way of seeing what an extended response question could look like. And it's exam 2, so you can stick it into your bound book. All right, so the function f is defined as follows. So we've got 1 plus x squared minus 1/5 x cubed, and it's been graphed for us, which is great. State the equation of the tangent of f at x equals 4. Now remember, this is in exam 2, so let's take note of the number of marks assigned. It's only worth 1 mark. So that means on our calculator, we can just go straight ahead and do our tangent line. So remember, you can do your tangent and your normal on your calculator. So we're just doing a tangent. Write the expression. So it's 1 plus x squared minus 1/5. So I'm just going to write that as 0.2. It's the same thing. X cubed. And we want it at x equals 4. and then it's going to give us our answer. Now these are terminating decimals, which is fine, but please do not round unless it asks. So you could write your answer like that. I'm just going to change it back to standard and leave things as fractions for now, if it's going to let me do so. All right, so there's our answer. So just remember, it is an equation, so it's going to be y equals. All right, moving on. So now it's a PDF, it's a bit more temperamental. All right, Newton's method is used to find an approximate x-intercept of f with an initial estimate of 4. Find the value of x1. So we just did Newton's method of approximation. So remember, it is on your formula sheet. Yeah, Newton's method. So basically we start off with our initial value, which is 4. So x1 is equal to 4. Oh, I just missed a question, didn't I? Let's finish this and then we'll go back and do the previous question. So f of 4 over the derivative at 4. Now, I have noticed that this is the second time I've used that function. All right, so remember we used the function to create our tangent, and then I'm using it here. So just to save time, I'm just going to look, and I'll see that I'll be needing it later on. So during reading time, that's something you might want to pick up on, because it's then easier just to define that function instead of typing it in individually. And I typed it in here, so I'm just going to be sneaky and cut it down there. Oh, what's wrong? All right, I didn't do define f of x equals. Okay, so there, I put it into my calculator, so I could have used that for the previous one. So when I went to calculate the line, I could have just put f of x in there instead of the whole expression. All right, so just like we did before, I'm going to just calculate f of 4. And then the derivative, so interactive calculation, derivative, and a derivative at a value, so I can just put in f of x, and we want that at 4. All right, and so then I can just do 4 minus, set up my fraction, and drag those numbers down. Oh, come on. Is it thinking? Shouldn't be thinking. All right, so we get 53 on 8. Now, again, that is a terminating decimal, I'm pretty sure. So let's just see. So if you were to write it decimal, just do all the decimal places. So 6.625. Don't write 6.63 because such an easy mark you would get wrong. All right, so leave it as a fraction, or write all the decimal places if it's a terminating decimal, that is. All right, so this is a terminating decimal. What I mean by that is the decimal places don't go on forever. All right, let's go back and answer question B. So usually on an exam, they might say sketch on the graph above. So they'll write something here so it reminds you to sketch it, but just make sure you take note of things like that. So in reading time, that's something you might need to take a mental note of, or once you've done a question, maybe cross them off, or look at the marks assigned to that question, and then, yeah, so you don't want to miss a question like that, like I just did. All right, sketch the graph of the tangent of f at x equals 4 on the graph above, labeling the point of tangency. All right, so we need to put the point of tangency and the x-intercept with the coordinates. So we just don't state x or y, we put x and y. All right, so you would need a ruler. So here's x equals 4, so our tangent goes through this point here. So obviously that has a set of coordinates, which we're going to have to work out. And then it's got an x-intercept, which we can also work out. So going back onto the calculator, so let's just find our tangent up here. All right, so I'm going to copy that. All right, so using solve, we're going to let that equal 0 to get that x-intercept. All right, there it is at 53 on 8. Now, just so we know exactly kind of where that is. 6, oh, it's the same as before, wasn't it? 6.625, so it's here. So again, we need to label that with the points. So 53 on 8, 0. And then for where it goes through the point, x equals 4. So 4, we just need to get the corresponding the corresponding y value. So again, we can just highlight this, drag it down, and do given that x equals 4, and we get 21 on 5. All right, and then obviously you need to draw a straight line going through them. This is going to be hard for me because I don't have a ruler. Whoops, that's very wonky. But please take a ruler. If you don't have a ruler, you need to use a straight edge to draw it as best, because I've gone under. Obviously, it shouldn't be going under. Maybe I should draw it again. I don't think it's going to be any better. Oh, look at that. That's all right. All right, do make sure it goes through that x-intercept. Doesn't say to put the y-intercept, and you can see that it's actually not going to go through that y-axis anyway. All right, so just make sure we've done that all. Yep, coordinates, fabulous. All right, let's moving on. Find the horizontal distance between x3 and the x-intercept of f, correct to 4 decimal places. So x3, we're using Newton's method of approximation again. So if we go back, you can see in the stem of the question, it's referred to it here, but I kind of think if it was on an actual exam, it would make reference to that, but yeah, so the x cubed, we're now just going to do another 2 iterations. So we already know, so we had x0 was 4, x1 was 53 on 8, and then we just keep going through on our calculator basically. So what was it, 53 on 8? Oh, so time consuming. I'm just going to go up here. 53 on 8. Actually, I'm going to pause and do it. Alright, so you can see on my calculator I did f of 53 on 8 and then the derivative. So just plugging it into your formula, remember it is on your formula sheet. So we're going to have 53 on 8 minus, now just because we've got e there, I'm going to just change it to a decimal. Oops, let's go here, drag this down into our numerator, drag this, oops, whole thing down to our denominator. Alright, so we get 5.757. And then we need x3, so we do the same thing again. So once you do that, I'm just going to give you the answer because it's very time consuming, 5.2397. And it does ask for the horizontal distance between x3 and the x-intercept. So our x-intercept, all right, so if I go back here, all right, so we need to work out this x-intercept. So basically we're just doing f of x equals 0. So that gives us x equals 0.0538. All right, you can do that on your calculator. All right, so we take x3, which is 5.2397, and take away 0.053. Sorry, I just deleted something and I think it probably jumped a bit. So 5.1859 is your answer, just making sure that you round correctly from your calculator. And using as many decimal places as you can. So like I always do, highlight and drag down, all right, to get the decimal places. All right, in question E, explain why Newton's method will not converge to the x-intercept of f for an initial estimate of 0 or 10/3. So you can't use Newton's method of approximation at a stationary point because your tangent will be, so let's just show an example. So your tangent would actually be a horizontal line. So when it's a horizontal line, it's actually not going to cross the x-axis. So the best way to explain that, say the gradient at those 2 points, so the gradient at x0 equals 0 and x0 equals 10/3 is 0. Therefore, the tangent line is horizontal and does not cross the x-axis. So that is also covered in the Ed Rollo video. So if you watch the Ed Rollo video, towards the end it says the exceptions when you can't use Newton's method of approximation. So you can't use it, you can't substitute in a value, your initial value, if it's at a stationary point. All right, so you can choose anything, but if it does not work, then, or if you don't get an x-intercept, it's because your tangent is horizontal. All right, where are we? All right, the area under the graph of f between x equals 0 and x equals 4 is to be estimated using trapezium rule approximation with trapezium of horizontal width 1. Find the approximation for the area under f between x equals 0 and x equals 4 using this trapezium rule approximation. So trapezium formula is also on your formula sheet, so you can see it down the bottom there. So xn minus x0, so xn is your end point, and x0 is your starting point, and n is your number of trapeziums. I was about to say rectangles, trapeziums. And here's your formula. So pretty much you're multiplying everything by 2 except for the initial value and the last value. All right, so the two end values don't get multiplied by 2, but everything in between does. All right, and you can just do it on your calculator. I mean, it's worth 1 mark, so you don't even have to put it on your page, but I am just to show you. All right, so our first value of x is 4, and our end value of x is 4, our starting value is 0, and 2 times the number of trapeziums. So they've got a width of 1, so that means it's going to be 4, so it's over 8. And then we do f of 0 plus, and then everything in between gets multiplied by 2. Oops, did multiply it by 2. And then your last value, so 4 is our end, does not get multiplied by 2, sorry. All right, because the 2 endpoints only get counted once if you think of the trapeziums next to each other. Something like that. This gets counted once, this gets counted twice, but when you're calculating the area of a trapezium, sorry, let me start that again. All right, so there's your two trapeziums. So if we're calculating the area of this first one, we're using this length and this length. When we calculate the second trapezium, we're actually using that middle length twice. That's why you're multiplying by 2. All right, so you can just plug that all into your calculator and we get 62 over 5. That is also a terminating decimal, which is 12.4. So either answer is fine. All right, so it's only worth 1 mark, so just doing it on your calculator is fine. Hence, determine the difference between this trapezium rule approximation and the actual area. So the actual area, now it's worth 2 marks, so just make sure you just do a little bit of working out. F of x has been defined in the question, so we don't need to write it out. So that is sufficient, and when you do that on your calculator, so we've defined f of x, that's a straightforward definite integral question, and we need to do the difference between the two. So we're going to have 188 over 15 minus 62 over 5. Now I don't know why we wanted to 2 decimal places, because it's actually a nice fraction, but there it is. I think it's 0.13 recurring, so just to 2 decimal places is 0.13. All right, on the graph provided on page 17, sketch for the trapezium used to estimate the area under f between x equals 3 and x equals 4. Coordinate points on the graph do not need to be labelled. So we're just going to add the trapezium onto here, which is a bit annoying because I've already put those coordinates on there. All right, so again, using a ruler. So I don't have a ruler. And I'm going to be going through there. Oops, that was very wonky. I should probably go through that point. All right, so there's your trapezium. And you can see how you're under the curve, so it's a little bit underestimating. All right, I think that's it for that question that I wanted to. Oh no, sorry, there was a pseudocode question. Oh, that's funny because this is a pseudocode video. All right, so here we've got a pseudocode involving the bisection method. All right, so we've got our inputs. So we've got f, which is our function, n is the number of iterations, a is your lower estimate, and b is your initial estimate. So we've already done a bisection method question, so it's going to be very similar. So you can see, oops. All right, so the pseudocode below is implemented. So there's our function. It's, is it the same one? Yeah, it's the same function as before. Sorry, there it is, keeps going. What are the lower and upper estimates used in the implementation as given? So it's just understanding this notation. So here's our f, and then we have our a, our b, and I can't remember what that was, n. Just make sure that's, oh, sorry, n is first. So here, n, a, b. So let's just change that to make sure that's right. So this was n, this was a, and this was b. So just be careful that you do have to pay attention to things like that. So your lower limit or lower estimate is 5, and your upper estimate is 6. So just reading that basically from that notation. What value will be returned when the algorithm implemented as given? Okay, so let's just scroll up. So we are going to n equals 3. So that just tells us how many, oops, iterations we're going to do. So I'm going to do my value of I. Sorry. So that's going to be our first iteration. And then, so we're going to do 3 iterations altogether. All right, then we've got our a plus b divided by 2. The f of a times f of mid. Sorry, this is all from above. I'll explain it in a sec. And then we change our value of a and b depending on the condition. All right, so we're going to assign, first of all, I equals 0. And then you can see here's our midpoint. So a plus b divided by 2, similar to before. So if you want to pause and try this question, because we've done a very similar one before. So a plus b divided by 2, if it's equal to 0, then that's our midpoint. If not, then we keep going. All right, so our first value of a, which I might just, is here, and b. So we did that in the previous question. So on my calculator, I haven't done this before, but I might just do it here. So a plus b divided by 2. And just so we don't have to keep writing it, given that a equals, and so first of all it's 5, or actually I don't know whether I can do comma, b equals 6. Alright, let's just type it in. Sorry, I thought it could have worked, but maybe it can work. I'm just not typing it in correctly. Alright, so 5 plus 6 divided by 2. So 11 divided by 2, we can do that easily, is 5.5. And then on our calculator, we've already defined the function, so I can just do f of, this is really frustrating, f of a, so this is our check. So f of a is 5 times f of your midpoint. So I'm just going through the pseudocode. So our mid was 5.5, which is what we just calculated. And basically we just want to know if that is, and that's a lot bigger than what I planned. I might have put in the wrong value. So to find it up here, but it's not, doesn't seem to be liking it. So let's just copy it again. I'm going to put it down here. Okay, so let's try this again. There we go, that's better. I don't know, maybe I defined something along the way. All right, so it doesn't matter whether it's what value it is, we just want to know whether it's positive or negative. So it is negative, so it's less than 0. So going up to our pseudocode. All right, so we're just basically doing this test. So it says if it's greater than 0, then we assign the midpoint to A, but it's less than 0, so we're going to assign the midpoint to B. So A stays the same, so it stays as 5, and B becomes our midpoint, which is 5.5. And then we continue the process again. So we do A plus B divided by 2. So that's going to be 10.5 divided by 2, which is 5.25 in our calculator. So I can just copy this down. Or you can just do it straight from there. So A is now 5.5. And our midpoint is 5.25. And that is not what I wanted. I thought it was going to be negative. Sorry, my A didn't change. Let's change that back. There we go. It's negative. I'm getting distracted by so many things outside the window. All right, because it's less than 0, A stays the same and B becomes our new midpoint, so 5.25. And then I start the process again. So I'm going to add A and B together again. So there's A and B, so you can see it's 10.25. So 10.25 divided by 2 is 5.125. And I'm going to substitute them into here. So A is still 5, but B changes to 5.125. All right, and now it's greater than 0. Now, because we're only doing 3 iterations, we don't have to really worry about the new value of A and B. It doesn't ask us for A or B, it's asking for what it returns. So it's returning the midpoint. So your final answer is this one here. So 5.125. All right, and I think that's the last question we need to do. All right, bye girls.